the class. So we are starting a different topic today. Whatever we have discussed earlier, this is slightly different from that one. Anyway, let me show you. So hopefully now you can see something on your screen. It should come. Yes. So now you can see. Just a minute. Who is coming in? Okay. So you can see here the title topic is sphere or cylinder in uniform external field. So two things, before I go into the details, let me make very clear. I mean, don't think this is a totally theoretical topic, although today what I will discuss is only theoretical. But there is something practical behind this one also. First of all, uniform external field. Now it is very difficult to have uniform field because uniform field means it is same, the field is same everywhere. That hardly happens. But here actually the concept is slightly different. That means, say I have a large volume, and in that large volume, somewhere there is a small, let's say, metal dust. Now these metal dusts, they are generated inside a manufacturing unit when we cut metal, because we have to cut a lot of steel and others in a manufacturing unit. So metal dusts are produced. And if we don't take enough precaution, this metal dust can go into the object or a machine or an equipment, and then it will remain there. Now, this metal dust being very small, typically we take it as a sphere or its geometry as spherical. Now, since this metal dust sphere that is very small, so just outside that metal dust, let's say up to 20 times the diameter of the sphere or 30 times the diameter of the sphere, if I take that volume, then within that volume, I can safely say the field is uniform. Because that volume will not be large compared to the large volume of the equipment. So therefore, I can analyze this case as a sphere lying in uniform external field. That means this metal dust, wherever it is inside the equipment, think about that, consider larger sphere, another larger sphere of diameter 20 times or 30 times of that small sphere, and in that larger sphere, but even then it is not that large because the diameter of the metal dust is very small. So even if you make it 20 times or 30 times, that larger sphere diameter is not very large compared to the overall volume of the equipment. Therefore, we can always assume that within that larger sphere of 20 meter or 20 times or 30 times of the spherical dust, the field is safely uniform. That is a good assumption. So it will not give us a big error. In the same way, there could be cylinders, like if it is a fiber, somewhat a small fibrous element floating in oil, let's say in transformer oil. So again, it's the same, that small fiber, we can take it as a cylinder, and then we can have a larger cylinder around it. Same way, diameter may be 20 times the cylinder, that fibrous cylinder. So again, we can safely assume that that cylinder is in uniform external field. So from this practical consideration, we are considering this topic. But we can I mean, in all practical cases, we can do it through numerical field computation. But I am going to tell you today that since here the geometry is very well defined mathematically, we can find a solution analytically. That means by directly solving the partial differential equation. So I am today going to tell you that analytical solution of field with these two examples, that is sphere or cylinder in uniform external field. I start with sphere in uniform external field. Now, this in this case, first of all, I will have to write the Laplace's equation in spherical coordinates, not in Cartesian. Now, equation 10.1, which you can see on your screen at the bottom, is Laplace's equation in spherical coordinates. As you probably remember, spherical coordinate is r, theta, phi. Now, how are you representing this sphere in uniform field? So here it is the sphere. So you can see that if we take the center of the sphere as the so-called origin of Cartesian, so XYZ is shown, then you can see that what is r, what is theta, and what is phi. So any point P, the radial distance from the origin is r. Then this r, if it is rotated with one end of r fixed at the origin, then the angle it makes with the positive direction of z, that is theta. Then if you take the projection of r on the xy plane, then you get this dotted line on the xy plane. And that line, where how much angle it makes with the positive direction of x is phi. So this is r theta phi. And we assume this is the external field that is of constant magnitude is 0, and this is acting towards the negative direction of z, that means top to bottom, but positive direction of z is from bottom to top. And the radius of the sphere is shown here, you can see it is a. The r is the radial distance of any point in the system from the center of the sphere. So with this configuration, we are going to solve this. For example, first of all, we will see that in this case, if you rotate r around the z-axis, that means when phi is varying from 0 to 2 pi, you can see that the entire configuration remains same for every value of phi. There will be no change in the configuration. So I repeat again that if you rotate this r around the z-axis in the anti-clockwise direction, that means phi is varied from 0 to 2 pi. The entire configuration remains same at every angle phi. So what we are saying is that this particular system has symmetry with respect to angle phi. That means it is independent of the coordinate phi. So in spherical coordinate system, it again becomes a two-dimensional system because the field is varying with r and theta and not with phi. So when we write the Laplace's equation, equation 10.1, we say that this third term, del 2v del phi square, will be 0 because v, that is the electric potential, will not be a function of phi. So Laplace's equation is modified to the first two terms. So equation 10.2 is the modified Laplace's equation. Of course, for this system, And what we are going to do here is that we are multiplying the entire system by r square, equation 10.2 by r square. That we have to clearly see that r is not 0. So I get 10.3. Now why I did this? Because in 10.3 you can see the two terms of the equation involve one variable only. That means the first term involves r, it does not involve theta. The second term involves theta, it does not involve r. When I have that sort of an equation, then this, of course, this is a second order partial differential equation 10.3, which directly coming from Laplace's equation. There is a way of solving this analytically. If you are mathematically, you have gone through all the mathematical methods, you know that there is something called method of substitution of variables. Method of separation of variables. That means we separate the two variables. So we are equation 10.4 is that approach where we are saying that the potential function, which is a function of r and theta, that is represented as one function mr, which is function of r only, another function in theta, which is function of theta only. So what we are doing is straight away we are putting, instead of v, we are putting mr in theta. So now, although it looks very big, but this equation is not very big. It is just simply substitution. And then in the first term, you can see that you cannot take the derivative of theta term in terms of r. So n theta comes out. Similarly, in the second term, you cannot take the derivative of mr with respect to theta. So mr comes out. And you get this second term here. And here we are going to do again that we are dividing by mr in theta, and we arrive at equation 10.5. Again, you can clearly see that the first term is involving r only, second term is involving theta only. Now why I did this? Because this equation 10.3, it also involved r and theta, but still this V, the electric potential, is a function of r and theta. Whereas in equation 10.5, the functional variable mr and n theta, they are function of a single variable. So now here I have two terms, a plus b is equal to 0, where a is function of r, b is function of theta. So there is no interdependence. So now we are going to solve. This is all mathematical. Everything is here. If you read, you can do it better than me, the algebra or whatever. See, so what we are saying that the first term being plus p, because a plus b is equal to 0. So we are saying a is equal to plus p, b is equal to minus p. So then, and of course, p is a positive constant. And there is a second solution that a is 0, b is 0. These are very standard methods of solution. So what we are saying, that first we are saying that this term a is 0. So we are saying that ddr of this is 0. I am not going into all that derivation. You please do it yourself. Ultimately, you see we get equation 10.8 where mr comes out to be this with two constants, C10 and C20. Of course, we have to find out this constant. Then second term is equal to 0. Again, we do all this, whatever is necessary, arrive at equation 10.9. And we find that n theta gets this. But now we have to look into this solution that whether it is valid for all values of theta. But we find that when theta is equal to pi, then this solution becomes undefined. But that's not possible. Why? Because we look at this. When theta is equal to pi, that means this r is just uh, at the bottom. But that at that particular point, field is not undefined. We have a field. I repeat, if theta is equal to pi, so rotate the r. You come at the bottom, opposite to positive direction of z. At that location, field is not undefined. Therefore, this solution, whatever we have got, has a problem that it is not possible to apply this solution at all points. So, what we are saying that this coefficient A10 should be 0. Otherwise, this is not applicable. Or in other words, we get 10.10. That is, n theta becomes this. And therefore, what is the electrical potential function? That is mr into n theta. So mr is 10.8 and n theta is 10.10. You multiply this. Then the first constant C10 multiplied by A20, that becomes C1 at the bottom. Then C20 multiplied by A20, that becomes the constant C2 at the bottom. So that's where it is written over here. A little bit complicated is when we take this first term, that means A plus B is equal to 0. So A is equal to plus P. Then we do this algebra and we find that this is equation 10.3. Then second term, B is equal to minus P. Again, we do all the algebra. So we arrive at equation 10.15, where we find MR is this. So you multiply these two and we get with R theta, which is, sorry, there is a typing mistake. This should be not in equation 10.15. It should not be r to the power minus 2. It should be r square. So you get 10.16. And therefore, we get the two solutions when we join together, we get equation 10.17. So what are the two equations? 10.11 and 10.16. 10.11 comes from the solution that A plus B is equal to 0. So A is equal to 0 and B is equal to 0. 10.16 is the solution that A plus B is equal to 0. So A is equal to plus B. B is equal to minus B. So we get the complete solution as equation 10.17. But now I find that we have to take a practical case. So we are saying a conducting sphere in uniform field. As I already said, that this is like a metal dust. Now, when I do that, at a particular, see, if this R is very large from A, somewhere here, look at my mouse, somewhere here, can I get the potential at this point? Answer is yes. How? Let's say the potential at the center of the sphere is V0. Then since it's uniform electric field in the z direction, negative direction of z, so potential difference will be field intensity multiplied by the distance. Since field intensity is vertical, so we'll take the vertical distance. So here at any point R, what is the vertical distance from the center of the sphere? It is R cos theta. So we say that the potential at any point when R is much larger than A is V0 plus R cos theta. V0 is the potential of the center of the sphere, and E0 into R cos theta, that means field intensity into vertical distance, is the potential difference between the center and that particular point. So that's very clearly is the potential when R is much greater than A. Now why I am taking R is much greater than A? Because at that location the perturbing action of the sphere is almost zero. That means the presence of the sphere disturbs the uniform field in around the sphere. But if R is much greater than A, then this perturbing action at that location is almost negligible. Now, if the sphere is charged, then a finite amount of charge Q will be there. So we can write equation 10.19. But in all practical systems, these metallic spheres are of floating metallic particles. That means they are not charged with a potential. So therefore, Q will be equal to 0. So what we get, that if I compare this with equation 10.18, so 10.17 here, that's the general solution, and then 10.18, we find that C2 becomes V0 because here it is C2, and here in equation 10.18 you see this is a constant term, so C2 is V0, and in equation 10.17 you have C3R cos theta. Here equation 10.18 you have E0R cos theta, so C3 is E0. C1 will be 0 for uncharged sphere, that I have already explained. So we write this equation, that is 10.17, after modifying it with the necessary field condition given by equation 10.18. But still I find that this coefficient C4 is unknown. So what I can do is, I can say that on the conductor surface, that means when R is equal to A, then this is VA theta, equation 10.21, when I have substituted R by A. Now, we know that a conducting sphere surface is equipotential. So at all values of theta, the potential must remain same. That means when theta varies, this second term should also be 0. But how is it possible? Then we say that this coefficient should be 0, and if you put that E0 into A plus C4 by A square is equal to 0, you arrive at C4 is equal to minus E0 into A cube. So therefore, the complete solution for electric potential in the domain R greater than A is given by equation 10.22. And if you want now field intensity components, you take the first order derivative, that is minus del V del R, that will become ER. You take the first order derivative, that is minus 1 by R del V del theta. If it is spherical coordinates, it is not just minus del V del theta, it is minus 1 by R del V del theta. So this equation 10.24. Now one thing we can clearly see that on the conductor surface, we know that the field lines are normal. That means there is no tangential component of field lines. Now E theta is nothing but the tangential component on the sphere. ER is the normal component of the sphere. Now if I put R is equal to A, that means on the spherical surface, I find that E theta becomes 0, which is exactly what is needed from the field conditions. And what is the normal component of field on the spherical surface? We put R is equal to A in equation 10.23. Then you get that it becomes 30 cos theta, and the maximum value of this is 3 times the E0. Now this is very, very significant. Why? Because particularly in a confined space within a say gas insulated substation or in a transformer tank, whatever be the field intensity at any location, if there is a metal dust, then because of the presence of that at the surface of the metal dust, the field intensity will become 3 times higher, which is too high, and therefore partial discharge will take place on the metallic dust particle surface. That is a potentially dangerous condition. Now, it could be a dielectric sphere in the uniform field. Now, you can ask me what is a dielectric sphere. The answer is very simple, that it could be a gas bubble in transformer oil, so which is very, very common. But in the case of a dielectric sphere, there are two different uh, dielectric medium. That means if this dielectric sphere is gas bubble, then inside the gas bubble we have air. Outside the gas bubble we have liquid. So we call it internal, where all the coefficients are written as C1i, C2i, etc. The other one is external, where it is written C1e, C2e, etc. Now we have to find out the coefficients. So again we take the same condition, that the potential at a large distance from the sphere, this is equal to this, which I have already explained, that V0 plus E0 r cos theta. So we can compare equation 10.27, which is for outside the sphere, with equation 10.28, and we can see, we can straight away find out these coefficients. In this case, C1e will be always 0 because dielectric sphere will never have free charge. So the solution for outside the dielectric sphere can be written as 10.29, where C4e is still unknown. Inside the dielectric sphere, the potential must be finite at all the points, which is quite obvious. And if you do that, then looking at the equation, that is equation 10.26, and once again just go back. See, this is a dielectric sphere. The center of the sphere is very much within the field. So field is not undefined at the center of the sphere when r is equal to 0. So that's exactly what we are going to put it here. So you can see equation 10.26, which is for inside the sphere. We say that C1i is 0 because otherwise at r is equal to 0, field becomes undefined. And in the same way, we say that C4i is 0. And then we say that C2i is V0 because we have assumed that the potential at the center of the sphere is V0. So we can write what is equation 10.30. But now we'll have to find out two different coefficients, C4e and C3i. How do I do it? We say that at r is equal to A, both these equations should give us the same potential because r is equal to A is on the surface, which is the boundary. So whether I calculate the potential from outside or inside, it should be same. So we write this next equation, and then we find equation 10.31 from here. But still it is not solved. So we go for the second boundary condition, that is the normal component of flux density. How do I get normal component? I take first find out the R component of field intensity since it is a dielectric sphere on the surface. The R component is normal component. So minus del V del R and then multiply it by epsilon and we get the normal component. For inside sphere for R is equal to A, and then we say that this is equal and we get one more equation 10.32. And now in equation 10.31 I have two variables C4e and C3i. In equation 10.32 I have two variables C4e and C3i, so we solve it and we get the two values C4e and C3i, and therefore I see that this is 10.33 is the solution for inside the dielectric sphere. 10.34 is the solution for outside the dielectric sphere. Now, looking at the configuration, you can see that r cos theta is nothing but the here r cos theta is nothing but the z coordinate. So just to make it a little bit interesting, I have written it in now in Cartesian, and then we see that this internal field equation 10.33 we can show it electric sphere as it is shown here in the figure. The electric field varies only in the z direction and not in x and y direction. And in this case, what is the z direction? It is the direction of the external field. So this question is often given that proves that the field inside a dielectric sphere varies only in the direction of the external field. So this is how you will have to prove it. And then what is that field intensity inside the dielectric sphere? Since equation 10.35 is represented in Cartesian, then we take the derivative in Cartesian form and we find that inside the dielectric sphere, the field is constant 10.36 because there is no xyz r theta etc in this expression. So the field remains constant. This is very, very interesting observation that inside the dielectric sphere, the field remains constant, although on the surface of the sphere there will be uh, disturbances or perturbations of the field. So this is what we have to show you, or you can expect questions in this form. And then if you look at this, the 10.36, you can clearly see that if you take the external dielectric as transformer oil, let's say 2.1, internal dielectric as gas, it is 1. So you can see that the equation becomes 3 into 2.1, then it is 2 into 2.1 plus 1. So you can clearly see that inside the dielectric sphere, that is the gas bubble, the field is higher than the external field. That means whatever be the field in transformer oil, the field intensity inside the gas bubble is much higher than that. And air is a inferior dielectric compared to transformer oil, so there is every possibility that partial discharge will take place inside the gas bubble. So you can see that although we are doing a very, very theoretical analysis, it is not just a theoretical analysis. There is very much practical aspect to it. Now, if I take a cylinder in uniform field, once again, this is the configuration. Only thing here, I have taken X in this direction, in the direction of the external field, not in the direction opposite to the direction of the external field. Rest of the thing is almost same. That is that r, theta, and z. That is the coordinate. But as you know that if it is a cylindrical system, we assume the field to be invariant in the z direction. That is, it does not vary in the z direction. And then we assume that the field is constant. of the cylinder in the this cross-sectional plane. So the Laplace's equation, which is 10.37, that third term is 0 because field is independent of field. So if we write equation 10.38, which is the Laplace's equation, but then in this equation, when we multiply it by r square, we find this becomes 10.39. As I said, that although the two parts, that is part A and part B on the LHS, looks like that they are involving a single variable, it's not so because V is function of R and theta. So we again go for separation of variables. So we take the same approach that VR theta, let's say it is represented by MR into M theta. And then again the same thing, that one solution will be A plus B is equal to 0. So A is equal to 0, B is equal to 0. So 10.41 is that equation that when we separate it into MR and M theta, so first term is involving MR, second one is M theta. So approach is exactly same as in sphere or as in cylinder. And then we say that part A is 0 and part B is 0, and we arrive at the solution, and we go ultimately find that the final solution for this particular case, that A is equal to 0 and B is equal to 0, is this. By the way, one thing I explained, that in 10.43, that means that B is equal to 0, that solution gives rise to this one, equation 10.43. Here it is A10 into theta. Now there is a problem here. That means theta, as you can see from here, is the angle as it is made. But now, if I rotate this R around this z-axis, then theta could be 2 pi, 4 pi, 6 pi, ultimately it could go up to infinity. But even then, this point is well defined. If you even rotate it 100 times or infinite times, this point remains same at a particular location. So there is a field at that location. But then if theta becomes almost infinite, then this equation 10.43 becomes undefined. So we take this first term A10 as 0. Otherwise, we can't get the solution. Then we take A plus B is equal to 0, that A is equal to plus P and B is equal to minus P, and then we go into all sorts of solution. And finally, we arrive at equation 10.52, which is the general solution for a cylinder in uniform field. After that, we follow the same logic. That means at a larger distance from the cylinder, first I of course taking the conducting cylinder in uniform field. So we say that at a larger distance, V theta is, VR theta is E0 plus E0 R cos theta, which I have already explained. So from that, I find that two coefficients can be obtained, C1 and C3, but still C2 has to be found out. Then we do the same thing as we have done in sphere. For R is equal to A, that is on the surface of the sphere, we write the equation of potential. And then we say that this potential has to be same at every value of theta. So the coefficient of cos theta must be 0. Therefore, C2 by A plus E0 into A is equal to 0. Or we get C2 is equal to minus E0 A square. So therefore, the solution becomes equation 10.54. So we can take their derivatives in ER minus del V there, E theta, 1 minus 1 by R del V del theta. And in the same way, we can check that the tangential component on the surface of the sphere, when we put R is equal to A in 10.56. So you put R is equal to A, you see 10.56 is 0. So that means tangential component is 0, which it has to be. Then what about the normal component? If you put R is equal to A, you see this is 2 is 0 cos theta. That means the highest value of that is 2 is 0. So just compare it with the spherical dust particles where the normal component on the conducting surface was 3 0. In this case, it is 2 is 0. Now this the conducting cylinder could be a small piece of wire that might be floating in transformer oil. But then we find that the effect of a conducting spherical dust particle is much more detrimental because then the maximum field intensity on the surface of the spherical particle becomes 3 0, whereas in the case of cylindrical conducting particle it becomes 2 is 0. So this sort of question you can also expect that compare uh, the highest value of normal component of field on the surface of a conducting sphere or a conducting cylinder in uniform field. Then you have to prove by these mathematics. Then we take the dielectric cylinder, that means a fibrous cylinder, fibrous impurity floating in oil. So same way we write two solutions, 10.58 is inside the cylinder which has a particular permittivity, and then equation 10.59 which is external to the dielectric cylinder which has a different permittivity. So again we start with the same concept, that is if the potential, if we take R greater much greater than A, do of electric function of 10.59 which is for outside the dielectric cylinder, and we find two coefficients. So we write equation 10.61 where one coefficient is still unknown. Similarly, inside the dielectric sphere, everywhere field should be finite. And if I apply that condition to 10.58, this C to I becomes 0. So you can see that this 10.62 becomes this. Why? Because at the center of the cylinder, I am assuming the potential is V0. So how do I find the two coefficients? 10.61 has C2E, 10.62 has C3I, two unknown coefficients. So again, same way on the surface of the dielectric sphere, the boundary condition is that the potential must be unique. So I put R is equal to A in 10.61, then I get the potential from outside the cylinder. Then I put R is equal to A in 10.62, it gives the potential from inside the cylinder, and they must be equal, so I get 10.63. But then still I don't get these two coefficients. I need one more equation. So again I go into the normal, again the weight is the normal component. So I take minus del V del R multiplied by permittivity is the normal component of flux density. So you can see this equation, left hand side is minus del V del R and then multiplied by epsilon E at R is equal to A. So this is the computation from inside the dielectric cylinder. And then minus del V del R multiplied by epsilon E at R is equal to A. So this is the computation for external to the cylinder, dielectric cylinder. So we do that and we get equation 10.64. So this is that one. So now we have two equations. What is that? That is 10.63 and 10.64, and we can solve, and now I have the two expressions of that coefficient. Then this I can put in equation 10.61 and then yeah 10.6 Inside the, yeah, external to the one, it is 10.61, and this internal is 10.69. So you put this coefficient point cylinder, 10.66 equal to the dielectric cylinder. Once again, if you look at this diagram, you see that r cos theta is actually the x coordinate. So if I write it, the solution finally that we have obtained, where it is here, as r cos theta is equal to x. So in equation 10.65, which is inside this dielectric cylinder, this r cos theta, when we write that is at x, we can see that the electric potential varies only with x. And what is the x direction? That is the direction of the external field. So you can see that this is once again that inside the dielectric cylinder, the field varies only in the direction of the external field. So this property is same as that of the dielectric sphere. And then if I take this, I mean the derivative in Cartesian del v del x, I find that the field intensity inside the dielectric cylinder is constant. So this property is also same as that of the dielectric sphere. But here now again, if you take the case that here it is given that, say here, if a cylindrical air bubble is trapped within a molded solid insulation of relative permittivity, say 4, that means we are using a epoxy resin and we are molding an equipment, but due to mistake, a small air bubble remains trapped. Now that will never come out, but now this will act as a gas bubble, that means dielectric cylinder inside a, I mean inside an external field which is made of the solid insulation. So 10.68, if you put epsilon e is 4, so numerator is 8, denominator is 4 plus 1 is 5, so it becomes 1.6. So you can see that the field inside the gas bubble is 60% higher. Whereas epoxy resin is much better insulation than air. So if this gas bubble remain trapped in epoxy, so what will happen? There will be invariably partial discharge in that gas cavity. And this will damage the equipment in the long run. So in this way, a few certain practical cases which happen in our life can be analyzed with the help of purely analytical solution, which I have tried to show you today. This, you will get the note. This note is, as you can clearly see, is very much mathematical, but that mathematics is nothing which you cannot solve. I mean, you can do that mathematics yourself. So that's for today. Uh, if you have anything to ask, then please tell me.
No, sir.
Okay. So then thank you very much. So you can log off. You can
Thank
log
you,
off.
sir.